Question 3, we have a stunt person who is falling, and they land on a mat. Let's imagine the alternative. They're landing on the ground. So the stunt man that's falling, or stunt person that's falling, has a velocity, and it'll be the same in both cases. So what's going to be different is they hit the mat or they hit the ground. So it reduces the kinetic energy loss. Well, kinetic energy is 1/2 mv squared. Well, the mat, is it going to change the mass? No. Is it going to change the velocity? It's going to change the velocity, but that change in velocity, the final velocity, is 0. Initially, it's some number. It'll be the same in both cases, and it will be 0 in the final case. So it's the kinetic energy is the mass and the velocity. It's going to go from some kinetic energy, which will be the same, to no kinetic energy. So whatever it hits, the change in kinetic energy is going to be the same. And for the same reason, the change in momentum is going to be the same. Now, it's not going to increase the momentum change. It's going to be the same. It shortens the stopping time. So if it shortens the stopping time, that means if the stopping time, let's say, is 1.0 seconds when it hits the ground, the stopping time will be less, like 0.5 seconds. That's actually not true. It doesn't shorten the stopping time. It lengthens the stopping time. So right off the bat, by eliminating all the false statements that we have, we're left with choice E. It does lengthen the stopping time, and it reduces the force applied during the landing. Well, again, we know the change in momentum is m delta v, and that is equal to the impulse is f bar delta t, and these two happen to be equal to each other. So by increasing the time, we reduce the force. If we have a same delta p, we are going to decrease the force by increasing the time. So we can positively show that it's the fifth choice.